Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss an important topic. The topic is consequences of the Lorenz transformation. We have already shown that some unexpected consequences follow from applying Einstein's postulates to physical situations. Now we use the more mathematical basis of the Lorenz transformation to show that these same consequences and others can be obtained. First, we discuss the relativity of time. Right? Now, I will draw a figure first, then I will proceed. You can draw the figure with me. So let me draw a figure. Let me complete the figure. Let me use another color. Let me make it neat. Let me make this bold. And this one bold. This is T1. This is T2. Let me use another color. This is my block 1. This is my block 2. This is X1. This is X2. And what else? This is T2 minus T1. This is my figure 1. Let this be part A. This be part B. Let me check it, then I will explain. T1 prime, X0 prime, U, X0 prime, T2 prime. This is T2 prime minus T1 prime. Then I have clock 1 and clock 2. And this is X1, X2, T2. Okay, our figure is complete. Let me now explain it. Remember, in the last lectures, we have discussed the time dilation, and we have derived the relation delta t is equal to delta t naught over square root of 1 minus u square by c square. Let me encircle it and name it as equation 1. Right? Remember, what is delta t naught? Delta t naught is time interval measured by an observer relative to whom the clock is at rest. And in our case, that observer is S prime, right? And this delta T naught is called, you know it, proper time, right? I repeat, we are discussing two observers, right? In the frame of reference of S, the clock carried by S prime observer on the train moves with speed u. U is the relative velocity of frame S prime with respect observer in frame S. You know that. So delta T naught is the time interval measured by S prime related to whom the clock is at rest. This delta T naught is called the proper time, right? And delta T is the interval measured by observer S, right? The proper time interval between the events, as we have already discussed, is the smallest interval between them that any observer can measure. Now, all observers in motion related to the clock measure longer intervals. Delta T is longer than delta T naught, right? And this effect is called time dilation. The observer relative to whom the clock is in motion, that is observer S, measures a greater interval between ticks, right? We have obtained this relation by applying, as we already discussed, by applying Einstein's postulates to physical situations. Now we will see that we can obtain this same equation from Lorenz transformation. This equation can be obtained as a consequence of Lorenz transformation. So for that, I have drawn this figure 1. Let me explain the figure. Now we have again a reference frame S prime and S. S prime is moving with velocity u relative to reference frame S, right? Now in this figure, what is shown here is a different view of the time dilation effect. Clock, this clock here, these all are clocks. Now clock C prime is at rest in the frame of S prime, who moves at speed u relative to S. S prime measures the time interval delta T prime. This is my delta T prime. S prime measures the time interval delta T prime equal to T2 prime minus T1 prime, in which the hand of the clock moves between two marks, passing the first mark at time T1 prime and the second at time T2 prime, right? The hand of clock C prime passing the two marks can be regarded as two events which occur at the same location x naught prime according to S prime, because clock C prime is at rest in that frame. Let me write it. This is important. The hand of clock C prime passing the two marks can be regarded as two events which occur at the same location x naught prime as shown in the figure. Clock C prime is at the location x naught prime, right? According to S prime. Why same location? Because clock C prime is at rest in that frame, right? However, let me move to the figure. However, S, whose reference frame contains a stationary set of synchronized clocks, observes the hand of clock C prime to pass the first mark at the location x1, where the local stationary clock reads time t1, and to pass the second mark at location x2, where a different stationary clock reads the time t2. I repeat, the frame S, whose reference frame uh, contains a stationary set of synchronized clocks, observes the hand of clock C prime to pass the first mark at the location x1, where the local stationary clock reads time t1, and to pass the second mark at location x2, where a different stationary clock reads the time t2. Now we can find, so we have here two intervals. T2 minus T1 is delta T, and T2 prime minus T1 prime is delta T prime. Remember, we've already discussed in the last lecture that at every location in frame S, we have a clock, and all clocks are stationary and synchronized, right? Now we can find the relationship between the time intervals delta t and delta t prime directly from the inverse Lorenz transformation. So let us move from the inverse Lorenz transformation. We have delta t is equal to gamma times delta t prime plus u delta x prime over c square. Let me encircle this equation. We've already discussed this equation here. We are just using it. This is our second equation in this discussion. Delta t is gamma times delta t prime minus u delta x prime over c square. This general expression gives the time interval delta t measured by s corresponding to the time interval delta t prime measured by s prime for events that are separated by a distance delta x prime. Now, according to S prime, relative to home, clock C prime is at rest. The two events. Which two events? The hand passing the two marks take place at the same location x naught prime as shown in the figure. So delta x prime is equal to 0, right? Now, because S prime is at rest relative to clock C prime, the time interval delta T prime measured by S prime is a proper time interval. So delta T prime is proper time, right? Which we represent as delta T naught. So substituting delta x prime equal to 0 and delta t prime equal to delta t naught into equation 2 into we get this our equation 2. So when you do it, this term will vanish because delta x prime is 0. So you will simply get delta t equal to gamma times delta t naught. Let me write delta t is equal to gamma times delta t naught, which is equal to delta t naught over square root 1 minus u square by c square. Let me name it equation 3. This is my equation 3. Because gamma is equal to 1 over square root 1 minus u square by c square. Right? You can see equation 3 is identical with equation 1. Equation 3 is identical with equation 1. This is our equation 1. This one. The time dilation equation. Right? So you can see how we obtained the time dilation equation directly from Lorenz transformation. So it is a consequence of Lorenz transformation. Now you need to remember the time dilation effect is completely symmetric. We write it, the time dilation effect is completely symmetric. What does that mean? You can guess it. It means if a clock C at rest in S is observed by S prime, then S prime concludes that clock C is running slow. Each observer believes that the other's clock is running slower than the ones at rest in the reference frame of the observer. You know, time dilation is often summarized by the phrase, which phrase? Moving clocks run slow. Moving clocks run slow. It is useful to remember this phrase, but do so with caution. The phrase indicates that a clock moving relative to a frame containing an array of synchronized clocks will be found to run slow when timed by those clocks. That is, only in the sense of comparing a single moving clock with two separated synchronized stationary clocks can we declare that moving clocks run slow. Let me write it. It is important. I will write it in red. The phrase, which phrase? This phrase indicates that a clock moving relative to a frame containing an array of synchronized clocks will be found to run slow when timed by those clocks. That is, only in the sense of comparing a single moving clock with two separated synchronized stationary clocks, can we declare that moving clocks run slow, right? I hope you got the point. Let me give you a homework problem. The question which goes like this. Suppose observer S fires a light beam in the Y direction. That is Vx is equal to 0, Vy is equal to C. Observer S prime is moving at speed u in the x direction, part A. Find the components Vx prime and Vy prime of the velocity of the light beam according to S prime. And part B. Show that S prime measures the speed of C for the light beam. Let me check the question. I will repeat it. Suppose observer S fires a light beam in the y direction. Vx is equal to 0, Vy equal to c. Observer S prime is moving at speed u in the x direction. Part A says find the components Vx prime and Vy prime of the velocity of the light beam according to S prime. And part B says show that S prime measures a speed of c for the light beam. This is your homework. Do your homework. Don't waste your time. And do not forget to subscribe and like my channel. This is all for today. Thank you. God bless you. Assalamu alaikum.